Hello everyone, my name is Phil Sturpey. I'm Principal Technologist at QA. In this Tech Week session, I'd like to talk to you about Amazon Web Services. Before we start, just a couple of points about housekeeping. Should you have any questions related to the session afterwards, please feel free to drop me an email at phil.sturpey@qa.com or the central box, which is posteventqueries.techweek@qa.com. And if you've got any questions during the session, just pop them into the chat window and then I'll come to them from time to time and pick them up there and then. As for what we're going to talk about in this session, I want to give you a broad overview of what the Amazon Web Services infrastructure looks like. So we're going to look at regions and availability zones. I'm also going to talk through a number of the services available, and there are many. I'll zero in on a particular service, which is EC2, and this is a service that delivers virtual machines. So we'll look at the role of EC2 services and AMIs, the Amazon Machine Images. We'll talk briefly about cloud storage and also about auto scaling groups, which is one of the mechanics used to deliver elasticity in the cloud. And finally, I'll talk about the 7 best practices. Now, these are actually Amazon's own 7 best practices, but they'll work with any cloud provider. When I tell people I work with Amazon Web Services, the first reaction is always, well, that's Amazon, they sell books, don't they? And yes, they do sell books. That's the big brand. But as a legend has it, that when they were sitting down to develop the web application, they knew it was going to be big, they knew it was going to scale. And so they thought about the back-end services first, so they could build a scalable, robust web application. And once they had these services, it made sense to them to actually package these up and sell them elsewhere. So what Amazon Web Services are doing is providing services not for your web applications, but to support your web applications. They provide infrastructure as a service. And what this graphic shows is that there are many services that Amazon Web Services offers. And in fact, that graphic doesn't touch half of them. The first inroads into Amazon Web Services for many people is that service at the bottom, which is EC2 or Elastic Compute Cloud. These are the virtual machines in the cloud. But there are others. If we think about storage for a minute, well, there's the S3 Simple Storage Service. This is just an object store where you can upload files into the cloud. It's classic cloud storage. But there's also EBS. Now, these are volumes which can be attached to virtual machines. They're file systems, if you like. From a database point of view, there's the RDS. This is a service which is a managed relational database service in the cloud. There's also DynamoDB. That's not actually shown on this graphic, although SimpleDB is. SimpleDB is being phased out, and DynamoDB is the way to go in this regard. There are some application services or backroom services, if you like. So there's the SQS or Q service, which in fact was the first one that Amazon actually created and released. Then there's a notification service, services that will help the overall application work and function. If you're trying to take a look at Amazon Web Services and get a feel for what they're doing, a good place to start is case studies. Now, all of these are organizations that are already using Amazon Web Services. Netflix are a big case study. They use Amazon Web Services heavily. And they've contributed to many of the case studies. But you've also got media companies such as BBC, IMDb runs off Amazon Web Services. See, many of these actually have websites at the front of them. But some organizations use Amazon Web Services for uses other than web services. Or websites, should I say. They have servers in the cloud. They have cloud storage. It may be a disaster recovery solution. As I say, check out the case studies. They're definitely worth a look at. Now, what I'd like to do is take you on a fly-around tour of the Amazon Web Services cloud and look at what we mean by regions and availability zones and where indeed these services live. So I just need to switch window for a second and jump into my browser. And if I just go into full screen here and start. Okay. So, although we're talking about the cloud, we're clearly not expecting us to believe that resources sit in clouds. No, they sit in data centers. So spread around the world are data centers provided by Amazon Web Services, and they contain the assets that we provision. So as we can see, there's quite a wide spread from the US west, such as Oregon and California, way over in the east we've got Sydney and Tokyo. If we just fly around here, we've got quite a lot of provision in the States. There are 4 regions in the States, and I'll come back to and deal with those shortly. But then there's Sao Paulo in South America, and there's Ireland for the EU, or Dublin should I say, there's Sydney, there's Singapore in Asia Pacific, there's Beijing and Tokyo. In fact, Beijing is the newest of the regions. Now Beijing, as well as this region here called GovCloud, are pretty unique. The GovCloud because it's only for the US government. In fact, if you're in the Amazon Web Console in the browser and are looking for places to put your assets, GovCloud will not be in the list, nor will Beijing. Beijing is the newest of the regions, and not because this is for the Chinese government, but because they've still not fully crossed the T's and dotted the I's on who will be able to use the data centers there and in what way will they be allowed to be used. But it's expected that in time, once they've come out of what they're calling their own beta stage, that certainly multinationals that have got a presence in China will be able to use the Beijing region. But for now, that won't show up in your consoles. So let's take a look at the US. There are a number of regions in the US, 2 in the West, 1 in the East. But I'll focus on just one of them because every single region is built in exactly the same way. Now, although if we zoom into Virginia, we can see that it has 4 what are called availability zones. The main difference between each of the regions is literally the number of availability zones there are. So for example, in the US East there are 4, in Singapore I think it's 2, Dublin it's 3. But the specification for these regions is pretty much the same. There are some subtle differences. For example, some of the newer services aren't available in all of the regions. So some services you'll find that aren't currently available in a number of the Asia Pacific regions, but that's been changed over time. You just have to keep tabs on that. So this is a, quote, typical region. It has a number of availability zones. Now, an availability zone in theory is analogous to a data center. So you can imagine each of those availability zones, all 4 of them, is each a data center. Well, in fact, it could be more than one data center, and Amazon don't disclose, and they certainly don't advertise the locations with large neon signs. So we can expect then that availability zone A in Virginia is 1 or more data centers. And these data centers are distributed so as not to be affected by the same power grid. If there's a failure with the grid, it's only going to take out 1 availability zone. They're close enough geographically and use fiber optic so as not to have any latency between them, but distant enough to be separate. As you can see from this level, there are a number of icons that are sitting within availability zones and a number that are sitting at region level. Now we'll get into these in a moment, but there is no presence in a region in terms of physical equipment. All the physical assets are in data centers, which are the availability zones. So a region is essentially a logical grouping of availability zones. So what that means is, in fact, if a thing is said to live in region, so we can just about make out a blue S3 bucket in the region, well then what that means is that the assets you place into that bucket are duplicated in all of the availability zones. So in fact, if any one availability zone, we need 2 data centers, are lost, those assets are still intact. One important thing to consider about availability zones is that the name availability describes its purpose. If you've got a fleet of web servers, you want a highly available solution. You want there to be a web application running. If all your web application servers were in the same building, theoretically you could lose the lot. But by spreading your servers across a number of sites, should any one site fail, overall your application is still running. So availability zones are a mechanic to allow you to do this. So if you had a fleet of web servers, as you can see at the lower end of the graphic, we have 6 web servers. 3 of them are in availability zone C and 3 are in availability zone D. Then should either of those zones fail, we've still got 3 servers delivering out content. And we'll look at how the auto scaling group, as it's called, manages that for us later. So let's take a look inside an availability zone. One of the first things you're likely to do in an availability zone is spin up one or more EC2 instances, and an EC2 instance is a virtual machine. These are the servers that you launch. In this case, we're launching them in Virginia. When you launch an instance, you have a choice. You have a choice which availability zone, in which region you'd like to launch it. You might launch an EC2 instance in Virginia A, and you might launch another one in Virginia D. You might launch a third in Singapore A. That's entirely up to you. When you launch an EC2 instance, you've got a couple of choices. One, the location clearly, but two, what type of instance or instance type. This dictates the size. This is the number of processor units, the amount of memory, the type of volumes attached to them. So you choose the ideal instance type, so essentially a hardware type, but you also then choose the operating system. Do you want, for example, Linux on there? Do you want Windows Server on there? Once you've launched an instance, you can also resize. Now, in the same way that in the real world, that would involve you taking a server, shutting it down, cracking the lid, adding in extra memory and so on, closing the lid, restarting, the same kind of thing would happen in the cloud, but actually dynamically. Essentially, if you said resize this machine from a medium to a large, all that's really going to happen is Amazon will launch a large instance, point you to the large instance and throw away the medium. So there's a consideration there about this local storage. Did you store any data on the local drive? We'll come to that in a moment. And the third consideration, the last consideration, should I say, when it comes to EC2 instances, is how are you going to pay? Now, the standard model is on demand. So as you launch an instance, based upon the type of OS and the type of machine, and also where, for example, Singapore costs more than Virginia, then you pay by the hour. So the instance runs for an hour. At the end of the month, you've paid for that instance for the hour. If it runs for 1.5 hours, you pay for 2 hours. You round up for the hour. Two of the mechanics are available to you, so you can pay on demand. You can pay in reserve. You can, in advance, reserve either low, medium, or high utilization for a type of machine in a region, which is essentially a commitment to rent that machine for a period of time. And if you say you're going to reserve an instance for high utilization, you're pretty much saying you're going to be running it 24/7, which if it were a web server is true. And the mechanic for a reserved instance is you pay up front a fee, and the fee you pay up front is based upon the type and size that you're going to reserve. But then what happens is your hourly rate is reduced. And so if you get your numbers right, if you reserve an instance of a particular size in a region for high utilization, if you take into account the upfront fee and the fee you'd been paying by the hour, by the time you tally it up at the end of the year, then it's been a saving of 44–45%. Another approach is spot. And this is unique, the spot market. This is aimed at using, as far as Amazon is concerned, any free capacity. If you imagine at any given time in a data center, there's going to be a number of instances, some kit that is not being used. And it's clearly worth it to Amazon to get a little amount of money for instances that are running than no money for instances that aren't running, if that made sense. And so what they do, they let you bid on machine types. I could say, well, for a medium Linux machine in Dublin, I'd be happy to pay 5 cents an hour, which is below the going rate. Everybody else is contributing to that figure, and so depending on what people are willing to pay for spare, if it's spare, may not be spare, for spare capacity, then that dictates the going rate. And then as the rate goes up or comes down, if the rate comes down to or below the rate you're willing to pay, and of those who bid for that kind of equipment, you were the highest, then that equipment will launch and you'll be billed accordingly. And incidentally, if at a moment's notice the instances are thrown away, which can happen because the rate has gone up, you're never charged for the last hour. So in theory, you could get 59 minutes of free compute. But you've got to design your apps to cope with a situation where servers get added to your estate at a moment's notice and get thrown away at a moment's notice. They tend to be for backroom processing, or perhaps can just deliver some extra capacity for your web layer. So that's EC2 instances, and this is, as I say, the first thing usually people get involved with when they move to the cloud. Now, sitting there off to the bottom left is an EBS volume. If you've got a server, clearly you need some disk storage or volumes, and there are two available. The virtual machines, these EC2 instances, live in shared tenancy on a physical piece of kit. They are, after all, virtual machines. And attached to those machines are drives. Now, they're known as instance drives or ephemeral drives. And the reason is that should a server be shut down and then started again, ultimately, if you have launched a server, that's just simply a piece of metadata that customer X has a server of a particular type in Dublin. If they then shut that down, well, then it's used by someone else. And in fact, if you start up what you call, quote, your server, you simply get another machine elsewhere. So consequently, any and all drives that are physically attached to these virtual machines are wiped whenever an instance starts. Now, the instance drives are free and they're very quick, but there's no persistence. If you shut down a server and start it again, which you may well do, it's going to be a different piece of kit. So if you need a volume, and often people do, that persists, then you want an EBS volume. Now, these are network attached, and you provision these independently and then assign them to instances as and when you launch them. So they're block storage, POSIX compliant. You apply any file system you like to them. You can attach multiple volumes to a single EC2 instance. What you can't do is share. What you can't do is attach an EBS volume to more than one instance at the same time. Although what you could do is have an EBS volume attached to one instance. When you're done, detach, reattach to another instance, which is something you may do when resizing an instance, for example. You can specify with EBS that you want a particular level of IOPS, or I/O per second. By default, if you just get a standard EBS volume, you're going to get in the region of about 100 to 120 IOPS. But you can request an EBS volume of a particular size and a particular number of IOPS, up to a maximum of 4,000. So you have a choice. You either use the instance store, which is physically attached to an instance, so it's going to be much quicker, or you go for the persistence of an EBS volume. It literally depends on the architecture. Now, if this were a course, we'd be having a quiz at this point, and I might have mentioned the minimums and maximums, which I didn't, so I'll tell you now. For an EBS volume, the minimum is 1 gigabyte and the maximum is 1 terabyte, which is ample, but it may not be enough. It may be that you want a volume which is larger, maybe for database storage, in which case you just simply provision more than one EBS volume and then you stripe them, but that is something that you would do at the software level. So perhaps if you were going to be using Windows Server, you may, within a Windows instance, attach to more than one EBS volume, and then within Windows you would stripe them with software. Another question, which I have already answered in fact, is what file systems could you use for EBS? And it's actually any that you choose. Amazon don't care. So if you went out today and bought a hard disk from a supplier, you'd be able to write any operating system down that suits you. It's whatever, I guess, would suit the operating system. So within an availability zone in a region, expect to see lots of EC2 instances and probably EBS volumes. And these instances might be application servers, they may be web servers. It's entirely up to you. Now, what you'll be able to see just off to the right hand side is an AMI, which is also yellow and rectangular. Amazon love boxes, that's their biggest metaphor. So the EC2 instance is a box, EBS is a box. An AMI looks like an EC2 instance, it's related. The important thing for now is it's living at region level. As I mentioned earlier, there are no assets. There's no physical representation of a region. A region is simply a logical grouping of availability zones. So really what that means in practice is anything that is said to live in a region actually gets duplicated across all the availability zones in that region. And so an AMI, whether you create it or Amazon creates it, is available within a region, for example, Dublin. And what that means is there'll be multiple copies, at least one per availability zone. So an AMI is a template. It's a template on which you base your instances. So when you come to launch an EC2 instance, you'll say, I would like an Amazon Linux instance, or I'd like a Windows Server instance. Well, that information for your root partition is living in an AMI. Now, those AMIs are actually stored in S3, which we'll meet later on, which is a bucket. Now, these AMIs are created and provided by Amazon, and they live at region level. The significance of the region level is important when you write your own. It's quite common for companies to write what's called a golden image, or create a golden image. And that involves them creating an off-the-shelf server from an AMI, and then installing their bits. Maybe they've configured a few frameworks and installed their web app, which they don't want to be doing every time they spin up a new server. So they get one server built exactly the way they like it. Then they can take a snapshot of that, and that then becomes an AMI, but it's their AMI. And this is where it lives is important, because if you create your own golden image or AMI, you get to specify where it lives, and if it lives in Dublin, you can spin up instances of that type in Dublin. If you want to be able to reproduce that elsewhere, then you're going to have to replicate that into other regions. And not only can you create your own AMIs, but vendors can too. So SAP can create their own. You might imagine the likes of Sage. Sage did used to do this, in fact, and Sage did create an AMI which already contained the software, and so you could come along, you could spin up an instance based upon that AMI. It already had Sage installed, and the price you paid per hour reflected the base OS and the fee for the license for Sage. So that's AMIs. And when you launch an EC2 instance, as I said earlier, the EC2 instance will be based upon an AMI type. Now, the AMI doesn't dictate the type of machine, so you could use that AMI in large instances or smaller instances, or this might be reflecting the fact that you may start small, and then if needs be, you could enlarge it, just resize the instance. A common requirement in the cloud is a relational database. Now, if you're going to mimic in the cloud what it is you do on the ground, well then what you might well do is spin up an EC2 instance with the appropriate operating system and then install your database. So for example, you could spin up a Windows server and then install onto it SQL Server. Alternatively, Amazon provide a service called RDS, which is a managed database service. Now, if you looked under the hood, you're going to find an EC2 instance with a proprietary database installed on it. But by going via the RDS service, that's all managed for you. And by managed, we mean they install the database. Now, when you spin up an RDS database, this involves you connecting to the RDS service and requesting an RDS database, and you specify the type: Oracle, MySQL, SQL Server, or Postgres. And RDS will spin up an instance of the appropriate type with that database system on. You can even ask for multi-AZ deployment. In other words, you want two. I want two servers, one's going to be a master, one's going to be a standby server. You specify which availability zones you want them in, and RDS manages the replication. Now, if you're doing this yourself, you'd be thinking about perhaps replication versus mirroring. That's not even a concern, because behind the scenes, what RDS is going to do is just block copy between them. Because in addition to having an instance with the appropriate with the appropriate database system installed, it's already also providing an EBS volume. So it just block copies from one EBS volume to another one. They also take care of patching. So if Oracle needs patching, SQL Server needs patching, that's done for you. Now, you still need to administer the database. You still need to administer Oracle or MySQL if that's your intention. But a lot of things have been done for you. The instance, the EBS volume, the replication. It can even automate backups. But you can interact directly with it. If it's an Oracle instance, it's an Oracle instance. So that's RDS. So far we've seen EC2 RDS. RDS lives in a region, at region level. Now, again, if this were a course, I would have fed you a bit more information and we could have had a quiz. But some of these we can answer, because I've answered a couple of them already. So which database platforms are supported? As I mentioned, MySQL, Oracle, SQL Server. Now this fly around presentation hasn't yet been updated to reflect Postgres. As for the sizes, we didn't cover this, but in case you wanted to know, it's 5 gigabytes to 3 terabytes, which is the maximum size of an RDS database. As for what are the benefits of a managed relational database, well, I guess that'll be up to you. It'd be what appeals to you from that. Is it the fact that they spin up the instances, or the fact that they replicate across multiple AZ, the fact that they patch? It's whatever appeals. So there's no right answer, no wrong answer there. So that was a look-see at some of the things that we would expect to see in availability zones. This is where the instances live. And it's clear that if you have an instance in availability zone B, or a database in availability zone B, and that zone fails, is destroyed, is lost for whatever reason, then whatever assets you have in there are gone. That's why it's advisable to spread your assets, have more. We'll come to auto-scan groups in a minute. Let's focus on some things that do actually live at region level, such as buckets and databases. And when I say databases, I mean a DynamoDB database, not an RDS database. So S3, this is an object store. This isn't a file system. This is an object store. You interact with it over HTTP. You make HTTP requests to put files up into S3 buckets or download them from S3, or indeed delete them. So it's not a file system. It may have folders, but that's purely metadata. Folder names are just prefixes on the actual file name. Now, if you have an account and you use S3 as an account, you can have as many objects as you like, unlimited objects. The only limits are that no object can be larger than 5 terabytes, and that if you are going to, in S3, have buckets, you've got a maximum of 100 buckets, which is plenty. A lot of organisations use one. For example, Dropbox is built on S3 and has one bucket. Everyone's objects, everyone's files are stored in one bucket, and they manage folders within it. There's high durability, 11 nines of durability via replication. And what that means is, the anecdote Amazon will give you is, if you imagined you had 1 million objects and waited for 10,000 years, then you might lose something. And that's the kind of thing a bean counter would come up with. But the replication is important. What's happening here is, you put something in a bucket, your bucket, in Dublin, and what's happening is multiple copies are made into each of the data centers within that region. And Amazon would say they could lose 2 data centers before they would start getting nervous. So that's S3, often store documents. It's a good use case for logs. If you're doing any monitoring and logging, once you've got a log, store your log in S3. If you want to take backups of EBS volumes or snapshots, you stick them in S3. Another thing that lives at region level is a NoSQL database, DynamoDB. On another earlier slide, you'll have seen mention of SimpleDB. Well, that's gone by the wayside now, and it's DynamoDB. It's a very fast NoSQL database. In other words, it's about key value pairs. A good use case here might be if you've got a fleet of web servers spread over multiple availability zones, they may store their session state, in other words, the shopping carts, in DynamoDB. They're very fast to retrieve. Once again, multiple copies are made, mainly for durability. So all of the blocks of data are duplicated in storage devices in every single availability zone. They're fast because they're actually stored on SSDs, but they're also fast because if you were a web server trying to retrieve information from DynamoDB, then when you retrieve the data, you'll be retrieving it from the copy in the data center that you're in. Let's talk about scalability. Let's talk about auto-scaling groups. This is a key component of working in the cloud, the ability to just spin up resources as and when you want them. If we take the scenario of web servers, which is a common use case, it's likely that you would put multiple web servers across multiple availability zones. Excuse me. I've got 6 web servers. Fine, I'm paying for 6 web servers. If they were all in the same availability zone, it would cost me exactly the same as if I placed them in 2 availability zones. And there's not that much more management involved in this. Optionally, I can put them in an auto-scaling group. If I just spun up 6 web servers and didn't put them in an auto-scaling group, if I lost any, if any failed, they wouldn't be replaced. But an auto-scaling group, one of its characteristics is you specify the desired level. And if you set the desired level to be 6 and 1 fails, well then the auto-scaling group will spin up a replacement. In the case of web servers, it's not enough probably just to have a group of web servers or a fleet of web servers, because there needs to be an endpoint for DNS lookups. If a client is looking for acme.com, or in our case qa.com, we want them to be able to hit any one of those 6 servers, or there may be 12 servers, there may be 18 servers. So we need a load balancer. Now that's another service that Amazon provide. You can have an elastic load balancer, or ELB, and that lives at region level. And that exposes a DNS endpoint. You can provide that to your DNS servers, so anyone looking for qa.com can point to that load balancer. It will have registered within it your 6 web servers. Now that you can either do that manually, or if those servers are in an auto-scaling group, you simply tell the auto-scaling group to register its instances with a load balancer. And then should the auto-scaling group add or remove any instances, it simply registers or deregisters that instance with the load balancer. And any queries against qa.com or acme.com will find existing servers, will not find non-existing servers. And the load balancer ensures it does it round robin across the availability zones. Another thing an auto-scaling group will do is, because it's a good practice to spread your load across multiple availability zones, is if you lose a server and it's lost from availability zone C, then the auto-scaling group will replace it in availability zone C. It makes sure that you've got an even number. But that's just about replacing those that are lost. What you can do with an auto-scaling group is scale out. Now this is either on a schedule. If you're aware that we get greater load in the evenings or maybe in the weekends, well then you can configure an auto-scaling group to, on a schedule, scale out. And this term refers to adding a number of servers. And then during quiet times, scale in. So either with a schedule, you can tell the auto-scaling group to scale out or in. And when you scale, you either add a number of servers or scale by a percent. You could scale out by 50% or 10%. Or you could resize to a set size. If you want your default fleet to be 6 servers, well then you can say scale to 6. But when you want to scale out, you might scale up by 2, another 2, another 2. And in fact, another scenario that's relevant is, rather than doing it on a schedule, you do it on demand or do it on load. If you could have a service, and the service would be CloudWatch, keep an eye on the CPU usage of your servers. You could set up an alarm that says, if the average CPU use for this group exceeds 80% for 5 minutes, well then it's clearly quite busy and struggling, so why don't we scale out? So the response to that alarm will be for CloudWatch to instruct the auto-scaling group to scale out, to add 2 or add 4 or add 10%, for example. And the auto-scaling group will do that. Remember, it will try and even it out across all the availability zones, those that you've specified. This only specifies C and D. And at the same time, it will then register those new instances with any load balancer. Now this can be done programmatically. You could write your own code to communicate with the auto-scaling group and call via the API to scale out, to scale in. Don't forget your load balancer, that routes the traffic. Now it does live at region level and it can balance across multiple availability zones. It does round robin, it keeps the load balanced across availability zones. It will detect unhealthy instances. If it performs a health check and detects that an instance isn't responding, it simply stops sending traffic to it. But it keeps performing the health checks. And should an instance become responsive again, that's great, it will start routing the traffic. But if that was an unhealthy instance in an auto-scaling group, the chances are the auto-scaling group would actually tear that instance down and replace it, in which case it would deregister it with a load balancer anyway. Another interesting point about the load balancer is it can terminate SSL. So if your traffic is coming in over HTTPS, then the SSL can be terminated there at the entry point to your fleet, and then that last hop to the individual servers, the servers aren't doing that decryption work and encryption work. And so that gives you a flavour of what an auto-scaling group is and its relationship with an elastic load balancer. The one thing not shown there is the role that CloudWatch plays. As I mentioned, if you don't want to work off a schedule, you can get CloudWatch to monitor metrics. And if a metric goes above a point or below a point, instruct the auto-scaling group to change. Now there are lots of other services that might operate inside regions or availability zones. For example, the queuing service. If you want to use a queue, so you could decouple your architecture, well, the queue would live in the region. There are some services that exist everywhere. So there's a service, for example, called IAM, Identity and Access Management. This is a service where you create your users and your groups for your AWS admins. Well, those users live across the cloud. So you don't create users in Dublin and have to replicate those into Sydney. If you've got an admin account or any kind of AWS account, that exists everywhere. So hopefully that's given you a flavour of how the AWS cloud is structured. The cloud is made up of regions, and each region is made up of availability zones. And it's these availability zones that are analogous to data centres. Where you put your assets either depends on where you are based. If you're a company based in the UK or in Ireland, indeed, you want your assets close by, that's where your users are. From a latency point of view, it makes sense to put it in Ireland. But from a compliance point of view as well, if you're an organisation and it's a requirement that the data for your application resides in the EU, well then you can comply. You can say it's in the cloud, and Amazon specify that if content is placed into a database in a region, it is not moved out of the region. That doesn't mean to say that you don't, with your application, retrieve data from your database in Dublin, place it in a web page which can be accessed everywhere. Yes, of course you can. The compliance and regulation will probably relate though to the database itself. You have a database, if you're putting it into the cloud, you want to know that it doesn't leave Ireland, or it doesn't leave Sydney, or it doesn't leave Sao Paulo. You notice incidentally on some of these regions they mention the city, on others they mention the country. So Ireland would be Dublin. So that was it for the fly around the cloud. That's the first half of this session. What I'd like to do now is just nip back to my slides. We've done the tour. What I now want to do is take a look at the best practices. These are the best practices promoted by Amazon for working in the Amazon cloud, although they do carry over to other cloud providers. So that's a list of seven best practices. I'm not going to read them off the list there, we'll just work through them one at a time. So the first one is design for failure and nothing fails. Clearly, everything and anything will fail. Drives themselves. A volume has an annual failure rate of 1 to 5%. So if you imagine you had a disk drive, anything you put on the disk drive, there's a 5% chance you could lose it. Servers fail, servers crash. Networks go down briefly. So if you factor that into your design, then you'll have an application, an overall application that can cope. So first aspect of this is avoid single points of failure. If you have a single database server, then you're clearly asking for trouble, because if you lose that database server, it doesn't matter how many app servers you have, how many web servers you have no application. So factor that in. Design it with two databases. Replicate between the two databases. Have your applications hit the primary database server. And if the first one fails, that's okay. You fail over to the secondary. It's part of your design. There was a failure. There was a serious failure. Your database server failed, but your design coped with it. Now, this could have been achieved with RDS, managed RDS database with replication between two availability zones. And if you think about the likes of, say, SQL Server connection strings provide for this exact scenario, and if the first server fails, they fail over automatically. There's nothing required at the back end. So design for failure, expect failure, and plan for it in your design. The second best practice, loose coupling sets you free. It sounds kind of like a statement you find on a motivational poster. But if you think about the architecture, your design, the more loosely that your components are coupled, the bigger they scale. Now, this is clearly a thing we want to achieve in the cloud. We've got a fleet of web servers, and behind them we've got a fleet of application servers. Maybe they're video encoders. How are we going to manage if we lose a couple of application servers or need to grow? Let's take a look at two possibilities. How about load balancing? There's your fleet of web servers and there's a fleet of application servers. And if they're tightly coupled, what this means is within your design, you've configured each web server to know about the identity, or let's say IP, of each app server. And that's going to present problems when you want to add app servers or you lose app servers, because you're going to have to go back and reconfigure the web servers. So the ideal plan there is to introduce a load balancer. We saw that earlier. But the context there was a load balancer between the clients or DNS servers and our fleet. This is another load balancer between the fleet and the app servers. So each load balancer has an endpoint, and you give that to the web servers. So every web server will hit the load balancer to say, put me in touch with the app server. The load balancer will know about the identity or location of each of your app servers. And if they were, for example, in an auto-scaling group, if that group grew, the auto-scaling group would tell the load balancer. And if that group shrunk, thanks to the auto-scaling group, it would deregister them from the load balancer. So we can just grow the web fleet, we can grow the app fleet, and it's perfectly scalable. And loose coupling has allowed us to do that painlessly. Another scenario might be another tier. Video processing. Imagine this was some kind of YouTube-like scenario. You've got your web application and someone's uploading a video. So there's the app tier that deals with the administration of that, any tags they want. We can check the content. Maybe we will update the profile. And then what we do, we want to process the video. Now maybe that takes some doing, that takes some time. And maybe there's a variety of different encoding options we want to go with. So maybe we have a fleet of video processing servers, but perhaps they're busy. We've got to allow for a scenario where we simply haven't got enough processing power for the videos, so we've got to be able to back them up. So what we could do is introduce a queue. So rather than go down the route of a load balancer, which means that an app server is going to try to find one of those 6 video processing servers, they may all be busy. So instead, they drop a message into a queue. Here's the idea of a video. It's sitting in an S3 bucket. First one to get a chance, could you drop that file down, encode it, and put it back unencoded? And then you tell each member of the fleet, if you've got some time, pop the next message off the queue. And then you may be able to grow the fleet. Maybe you can't grow the fleet, but you'll just work through the queue. It's decoupled. In fact, video processing servers is a great use case for Spot. So you'll have the bare minimum 6 servers. If you can get any cheap compute, you'll add some more. And they can also read the queue, and eventually that queue will drop. Or you could put that in an auto-scaling group. So 2 examples of how you can introduce loose coupling into your architecture to really take advantage of what the cloud can do for you. So hinted at already, and even mentioned in passing actually, the third best practice, which is implement elasticity. You can clearly, at the push of a button or an API call, spin up additional servers. So factor that into design. We've already seen the fact that you can have an auto scaling group, and based upon demand, you can scale out, add 2 servers, take away 2 servers. But this point goes deeper than that. Don't assume their health, availability, or fixed location of components. Sure, servers fail, they might get replaced. So any given time you may not have the number you expected, but an auto scaling group could replace those. But they may not come back in the same place, they may have a different IP. If you have load balancers in the front rather than you've noted the IP address, well then it doesn't matter if the replacement comes up elsewhere. Now if you're talking about a design where servers are going to fail and restart, you really need a design that's resilient to reboot and relaunch. If you've got a design that says that to set up a web server, you spin up a server, configure it perhaps by configuring Tomcat or IIS by setting a few options and then dropping the web app into a folder. Well, that's a lot of effort. And what's more, if that's going to have to happen at 2:05 in the morning, it's going to be a problem. You can't have a design that relies on a human pushing buttons or running things. Better that you automate it. Now, the term Amazon would use is bootstrapping. So what you can do when instances launch is use a feature called user data. This allows you to pass scripts, and this can be automated. You can tell auto scaling groups what user data you want to use. So when the instance launches, user data or a script is passed in. This could be a bash script, it could be a PowerShell script. And when it launches, on demand on a schedule or because load is increased, a new server launches, any config is carried out automatically via a script, it's done, it's up and running. So certainly favour dynamic configuration, no manual processes. In fact, manual processes are an anti-pattern to the cloud. Security at every layer, here's another best practice. There are a number of services and mechanisms available in the cloud that come under the heading of security. And this could be to do with network security, it could be to do with permissions. Let's take data. There's a lot of data being used in the application. At any given point, that's either at rest on an EBS volume or in an S3 bucket, or it's in flight traveling between application layers, the web servers and app servers, or the user. So it's possible for you to encrypt data in transit if everything goes over HTTPS. It's possible for you to encrypt at rest. Now, an EBS volume is your responsibility. If you have an EBS volume, a drive, attached to an instance, it's a file system. Amazon have got no access to that file system. They don't know what file system you're using. You're in control. So if you have files on an EBS volume and you want those files encrypted for whatever reason, then you encrypt them. Use whatever software tools you might use on the ground, use them in the cloud to encrypt those files. If you want them encrypted for transit, well, one thing, you could do everything over HTTPS, and or you could encrypt the data before it's sent. That's just an application, it's just a task, it's a feature of the application. Principle of least privilege. So whatever it is you're doing, any service you're interacting with, when you start giving out permissions as admins, you should give out the least privilege. Now, Amazon have made that very easy for you, because what they've done is whenever you create what's called an IAM user, it has no permission whatsoever. You've got to grant it permission. And you have to be careful that you don't immediately make it an Amazon admin, that you just decide what permission you want individual users to have. Another layer would be security groups. Now, whereas the second point there was talking about privileges or permissions for admins to carry out certain tasks, like, for example, launch an instance or upload a file to S3. Security groups are more interested in the instances and the network traffic. They restrict traffic into or out of servers. And another consideration that's supported by by Amazon is multi-factor authentication. So when you sign up for an account with Amazon, you use an email address as an ID, you supply a credit card, and that's it. So from then on, when you sign in, you simply sign in with an ID and a password. Best practice says use multi-factor authentication. Now this involves you using either a Gemalto token, which looks like a key fob, or it's an app on a smartphone. And that will give you on demand a 6-digit number. And if you've associated MFA with your account, or indeed IM users, it works at any level, then when a user is attempting to log in, after they've supplied the ID and a password, they'll then be prompted for the 6-digit number. And this is a different number every time. It's not random. In fact, when you sign up for MFA, a long sequence of predetermined numbers has already been generated. And once Amazon knows the sequence, it will be able to predict what the next number is going to be coming out of your app. So there are a number of layers where you want to think about security. What you're going to do with the data, what you're going to do about permissions for users to administer the cloud, how you can restrict traffic into or out of servers, and certainly use multi-factor authentication along with your credentials. Just a couple more best practices. Don't fear constraints. This is definitely something for a t-shirt. Don't fear constraints. We fear them all the time. We're thinking about a design and realise, oh, hang on, there's a maximum size for this kind of machine. And my design is limited in terms of the RAM it can use. So I need a design that can cope with a maximum of such and such a memory. Now, over time, they're always going to be adding instance types that have more memory, but you can't wait around for that to happen. Or there's a maximum number of IOPS on a volume, for example, under a database. If we're thinking about RDS, RDS is based upon EBS volumes where the files go. The maximum IOPS for an EBS volume is 4,000. What if you need more? Well, have more than one volume and strap them together. That's going to give you multiple IOPS. What about failure? What if the server fails? What am I going to do if a server fails? Throw it away. If what keeps you up at night is thinking, what if that server fails? You need a better design. You need a design that if a server fails, there's nothing on there that can't be recreated. That you can simply start up a replacement server. There may be some kind of script that bootstraps it. So design accordingly. Don't have a design where you are constrained by the amount of RAM available on a particular instance type, or the fact that an EBS volume will only give you 4,000 IOPS, or the fact that if a server failed, your application would struggle. Think outside the box. And what that leads on to is the next best practice, which is think parallel. Consider a job that is going to take, in this case, 4 hours. If it was video encoding, let's talk about that again. I've got a job, it's going to take 4 hours. Now that in theory is a constraint. It's a 4-hour job. That's how long it's going to take. Well, if that job took 4 hours on an EC2 instance, well, not only does it take 4 hours, but you're being billed for 4 hours. But if you could break that task down, if we're talking about video encoding, is it possible to take a source video, chop it into 4 pieces, and encode them separately and stitch them together at the end? In which case, we'd have 4 instances, not 1, running for an hour each, not 4. And overall, we still spent the same money. We still had to pay for 4 compute hours, but actually the job got done in 1. Thinking outside the box, think parallel. Last best practice, leverage many storage options, which is a bit of an odd one, but it bears looking at. That in the cloud there are many different services that come under the heading of storage. Although actually, to be fair, Amazon distinguish between storage and database. Database would be DynamoDB and RDS. And storage would actually be the likes of S3 for the object store and EBS for the block store. But in this context, they mean all of those collectively. That if you've got a design and you're moving up to the cloud, oftentimes you tend to recreate in the cloud what you've done on the ground. So on the ground, my web server has files, and those files are stored on a disk drive. So it makes sense for my web servers to have an EBS volume available, and I'll drop the files in there. that's fine. But if you're talking about a fleet of web servers, then that will be a lot of volumes all duplicating the same files. And we can't share an EBS volume with a fleet of web servers. So maybe we start to think of, okay, well, let's put them into S3 instead. That's an object store. It's not a file system, but we could still link to and retrieve individual files if need be. And S3 will be available to the entire fleet of web servers. So imagine these are PDF documents perhaps. Instead of having multiple EBS volumes with a folder full of PDFs, we could instead say, well, let's put them in S3. Or maybe think out of the box completely and say, well, let's take the data from each PDF and store it in a database. And then use a key to look up the data for a particular file, and when they want the file, you simply stream back that content. So there are different types of databases. Object store, S3. Block store, EBS and instance types. It may be a relational database. I'll come back to that in a minute. NoSQL. If it's a NoSQL database you're interested in, well, that's going to be, as far as Amazon are concerned, DynamoDB. Just a point on relational database. You may decide to roll your own. You may decide to install SQL Server on an instance in the cloud rather than go for RDS. A common excuse for doing that has been in the past, anecdotally, where people have been worried about their exit strategy. If I spin up an instance, run SQL Server, then I feel more confident about taking that data away if I want to move away from Amazon. Well, if you put that into RDS, it's still a SQL Server database. The file system is still the same. So it is a relatively straightforward to exit Amazon in that case. So don't worry on that front. The last one in there, which is actually the second point, is edge caching, content delivery. And this is a specific scenario that Amazon have a service called CloudFront, which is a content delivery network. And what that does is that sits in front of your web app, and then when a request comes in for web content, it caches that content closer to the user. If you picture the map from earlier for a minute with those regions, in addition to those regions, there are edge locations, and currently there are 52. But that number is probably out of date by the time you listen to this video. 52 edge locations around the world. So for example, there's one in London. Well, there's certainly not a region in London, the region's in Dublin, but there is an edge location in London. There are edge locations in Italy, in Germany, in France, all over the world. There are always edge locations close by a region, but there are others as well. Now, these are not for the storage or hosting of EC2 servers, RDS servers. They're purely for caching web content. And what will happen is, imagine you've got a web app, and that web app is in Dublin, and a client requests a web page from your app, but from Sydney. Well, what will happen is that if you've got CloudFront in front of your web application, CloudFront will request a page, CloudFront will take that content, copy it to the edge location, not region, but the edge location in Sydney, drop it there, and we'll keep it there based upon the time to live of that content, and then serve it up from there to the user. Now, anyone else in and around Sydney, so anyone in Australia, New Zealand, who wants that page and is going to Amazon to get it, CloudFront will realise that it's got a local copy and will serve it up, and therefore serve it up a lot quicker to the user than if it had to go back to Dublin for it. Now, there are clearly issues around, does the data go stale? So you need to think about the time to live. For some content it's appropriate to cache, some content it isn't. So that's definitely a service worth looking at. The reason it's mentioned here on this slide when we're talking about storage options is, if we're talking about a web app, it may well be that you're thinking about how you might store the CSS files, the JavaScript files, the icons for your website. Do you store them on the web server, or do we stick them in S3? Either way, if we put CloudFront in front of that, then that content can be copied and cached local to the client. And in fact, there are a couple of use cases, or examples should I say, of using CloudFront. One's where you have static content, everything is completely static, and one is dynamic. And the static scenario, in fact, doesn't involve an instance at all. You don't need a web server. For static content, you take all of your web pages, stick them in an S3 bucket, and point CloudFront at it. And it's for that reason they've mentioned leverage many storage options here. Think about static websites, if you have any, the fact that you can go into a bucket rather than spinning up an EC2 instance and then running perhaps IIS just to look after a static HTML page. And that was the last of the best practices. So just to recap what we've covered in this session, I gave you a fly around the regions of Amazon Web Services, mentioned a couple in passing, including EC2, RDS, S3, EBS and so on. We looked at the purpose of the availability zones and also looked at the significance of services living in availability zones or services living in regions. Spent some time looking at auto-scaling groups and load balancers to understand elasticity. We then spent some time there looking at the 7 best practices, which included looking at a variety of different storage options. So we certainly looked at quite a lot of cloud storage. And that's it. Hopefully that session's proved useful and you've learned a lot about what Amazon Web Services is, where they are, the kinds of things you might do with them, and some of the best practices. But there's clearly a lot more that we could talk about and should talk about beyond the scope of what we can talk about here. So as for next steps, if you need to know any more about Amazon Web Services from a training point of view, you can come to the QA site, qa.com/Amazon, or just go to qa.com and pop Amazon in the search box, and that will list all the courses that we have on Amazon Web Services, and we have several. One thing to point out there is, as far as Amazon's curriculum is concerned, because they are indeed Amazon courses that we deliver on their behalf, there are 3 tracks. So Amazon think in terms of the architecture track, the sysops track, and the developer track. A developer track is hopefully quite straightforward. It's aimed at those people who want to develop apps that either run in the cloud or interact with the cloud. So admin tools, apps that are going to interact with the services. So how do we programmatically interact with S3, EC2 and so on. The architecting track is for those looking to look at how you could design an architecture, how all these services fit together. And finally the sysops track, and that's for the people managing that architecture, managing those services, tagging them, logging them, backing up and so on. And I say track because for each track ultimately there are going to be 3 tiers. So the associate or intro level, then the advanced and so on. So any interest you have in any courses, pop onto qa.com, search for Amazon and you see all the courses that are available. Other next steps, well, if you want to know more, Amazon have got a wealth of information, and if you can't remember these URLs, you can't go wrong by Googling AWS and case studies, or AWS and white papers, or AWS and user groups. Between the case studies, white papers and articles, you're going to find a wealth of information there. There's also a link for training there, so if you go to amazon.com training, it will list all the same courses that we deliver at QA. QA are the sole partner for Amazon in the UK, so if there is a course, we do it. There'll also be a link there for accreditation, so if you would like to take an exam, there are links to the various exams. We're not a testing centre at QA, you want a criterion centre, but you'll find a link on the webpage. So you come to QA for the training and then go to criterion for the exam. And so with the session at an end, it's at this point I'd throw it open to questions. But in fact, this is a re-recording of the session. On the day I had problems with microphones and it was a bit challenging. There were some questions, but as I clearly don't have an audience at the moment, there's not a lot I can do at this point other than to remind you that should you have any questions, please feel free to email me at phil.sturpey@qa.com whenever you view this video. And first chance I get, I'll reply and hopefully answer the question and point in the direction of any further information. So can I thank you for taking the time out to watch this video, I'm Phil Sturpey, Principal Technologist at QA, and this has been an introduction to Amazon Web Services. Thank you very much.